Hi everyone, I'm Jules. I'm a software engineer at Facebook in London, and I work on the Infer team. So Infer is not that. How does that work? Sorry. Full screen? No. Definitely not. Play. Thank you. Why did it? No, that works. So Infer is a static analyzer. It's open source, so you can find it on GitHub. And it ships with a number of analyses by default that do a range of things. The most advanced of which is a memory safety analysis that tries to flag bugs about null pointer exceptions or memory resource leaks or double free or the like. And it also has simpler analysis all the way to linters that there's even a small DSL to define your own syntactic checks on the code, for instance. And one of the defining characteristics of the more complex analysis in Infer is that they are inter-procedural. So that means they are able to flag issues that involve several procedures at once, possibly in several files. So in the rest of the talk, I'll explain a bit about Infer's architecture and how it does inter-procedural analysis at a high level. And I will also explain how we deploy it at Facebook, where it does diff time analysis. OK, so Infer starts from a project, which is some source files and a build system to build these files. And it's architectured like a compiler. So first, there's a front end that takes source code in the source language, so Java or languages supported by Clang. And much like a compiler, it translates them into a much simpler and common to all languages IR that is called SIL. And SIL is much simpler than Java or C++. It's just basically loads and stores and function calls and go-tos. Then once all the source files have been translated into Infer's language, the backend analysis run. And for each procedure, they compute a summary of the procedure in isolation of all the other procedures. And they are stored as what we call specs. So there's one specification for each procedure. And this is also the point where errors are flagged. So most of the analysis work by trying to establish that the procedure has no bug. And when there's a failure in that proof, then a bunch of heuristics kick in to classify the failure of the proof either as a weakness in the analyzer or as something that looks more like a bug that we should report. And so at the end of the analysis, we collect all these issues we found and we build a report. OK, let's zoom in into the front end, how it works. So there are two front ends, one for Clang languages and one for Java. I will describe them both. So we start with the project, the source code, and the build system. And now we need to find where the code lives. So we ask the build system, actually. So the way you would run Infer is just typing, for instance, infer -- make, and Infer will do all the work of figuring out what to do. And the way it works is it runs the build system and capture calls to the compiler that happen during compilation. And so it records for each source file it records that allows it to discover which source files should be analyzed and how they are compiled. And so it's a bit of it's not the most robust part of Infer because you have to do this work for each build system. All the build systems are different, and there's no sort of unified way to extract the information of how to build files given the build system. So that's a bit annoying. If you know solutions to this problem, please talk to me. But we have integrations for a few build systems, and that works. So if it's a Java file, then we call javac to get Java bytecode. And then our Java frontend actually starts from the bytecode and not the Java source, and translates Java bytecode into SIL. And if it's Clang, then we run Clang to compile the file, and we attach our own Clang plugin that dumps the Clang AST in some serialized format that our front end is able to read from OCaml and translate also into CL. And there's also the place where we plug our Clang linters. So because here we see the AST, we can run this source code, very syntactic analysis that just matches nodes in the AST and makes some reports. So we're able to do that for Clang, but not for Java, because Java we start at the bytecode level. So there's no linters for Java in Infer at the moment. So that was the front end. Let's look at the backend now. The backend takes procedures that were translated by the front end, and it tries to find specifications for them. So there are many analyses in Infer, as I said. They're all based on the same architecture that is compositional and on demand. So it's compositional. That means that it will schedule the analysis to look at each procedure in isolation without looking at the calling context of each procedure or the arguments with which the procedure is called. So the analysis, each analysis has to be smart enough to be able to work on a procedure without knowing anything about where it's called. And in exchange, that allows us to reuse the summary computed for the procedure in all the calling contexts. So that allows Infer to scale very nicely. And the architecture is also on demand. What I mean by that is that each procedure is only analyzed if it's needed for the analysis, and it's analyzed when it's needed. So let's look at an example. I'm going to use the allocates memory checker that we have as an example. So that's a checker that reports whenever a function is allocated with no allocation, like goo here. But it calls a function that eventually allocates memory. So let's see how this works. So let's say we're only interested in analyzing the functions in foo.java. So we start with one of them, like foo. And we see that it calls bar. So we need to compute the summary for bar first. So we go do that. Notice that bar here is another file. Also, I've written this as more or less Java code, but it's actually in the intermediate language of Infer. So Infer analyzes bar, and it noticed that it allocates memory on line 3. So that's the summary it computes. It remembers that the only thing it will remember about bar now is that on line 3, it allocates memory. So we come back to foo. And now we know that foo also allocates memory and we record the reason why we think it allocates memory, and that's because it calls bar on line 3. The reason we recall the reason why there's a bug is because when we're going to report later, it's going to be very important that we give some idea of why there's a bug to the user. So then we look at goo, it calls foo. And so we go look at foo and see that its specification says it allocates, so goo also allocates. And because goo is marked no allocation, we report here. So note also that in goo, we only recall that it calls foo, and we don't follow all the chain of explanation. This will be reconstructed only when needed, when we report, so that it scales more. Okay, so that's on-demand analysis. But interprocedural issues. And so one thing we were wondering at some point is how important is it that the analysis is interprocedural, And so we did this case study of bugs that were reported by Infer recently. And we counted for each of them if they were interprocedural. So we sorted them in 3 buckets. One is bugs that you can find just by looking at one procedure in one file. The second bucket is bugs you can find by looking at all the procedures, but only in one file. And the third category is bugs that involve multiple procedures that span multiple files. And what we found is that for some bug types, the majority of the bugs were in the last category. So it's very important. So being interprocedural and interfile gives the best signal to developers. So this is allocates memory that we saw, and this one is a bit particular because almost all the bugs it reports span multiple files. And all the way at the bottom, there's a byte pointer comparison, which is a linter, and so a linter only looks at the AST of one file. So unsurprisingly, it only reports intra-procedural bugs. Anything else I wanted to say? No. Okay. So how do we deploy Infer at Facebook? So I said it reports at diff time. So whenever a developer sends a new change, it will go through our CI system, and our CI system runs a bunch of tests, and it also schedules an analysis via Infer. And this happens all at the same time as human reviewers are reading the code and making comments. And so Infer is commenting on the diff just as other human reviewers will. So if it finds the bugs, it reports it on Fabricator, which is our code review tool that's also open source. And Infer comments look just like other human reviewer comments. So in that case, that's a report generated by Infer that says that there might be an old reference caused by the diff. And one important point is that in this integration, Infer, we only surface the bugs that Infer finds that were introduced by the diff, and only if they were in files that were touched by the diff. And the reason we do that is that that's what the developer currently has context on and is working on this change, and so is able to act on these warnings much more than on warnings about unrelated things. So at some point, Infer is happy with the diff, and all the code reviewers are happy about the diff. And so then it makes it into the code base and into our products. So let's go back to our example and see how diff analysis works a bit more in details. So let's say that our diff was the diff that introduced the call to foo in the no allocation method. So that's the state of the code after the diff. That's what we saw earlier. So we know that Infer does this on that version of the code. That it reports the error on Goo because it calls foo that allocates. So then what Infer will do is it will analyze the base commit, the version of the code without the diff. So in this version, Goo doesn't call foo. And also we need to reanalyze foo.java because that's the file that was modified. So Infer analyzes foo again. It needs bar. It already has a spec for bar. This one doesn't need to change because we know that bar hasn't changed. And so it will compute a get that foo allocates via bar. And then when it analyzes Goo, it sees that it does nothing. There's no allocation there. So now that it did these two analyses of the base and the diff, it knows that on the base there was no report. On the diff there was this one report about foo. And so what it will report to the user is what was reported on the diff minus what would be reported on the base. So it will report the new error. So this diff-based deployment model has been quite successful so far. We find that it helps developers move fast and give them more confidence about their code changes, because Infer will check that they don't introduce too many bugs. It also makes life easy for us because it makes it very much easier to deploy new checks because we only report new bugs introduced by diffs. So even if a new analysis that we ship has a legacy of thousands of bugs in the code base, we don't need to care about this right now because developers will not see them because they were already there. They will only see the new ones that they introduce. So we find that quite valuable. For instance, another situation that's not like this is compiler warnings. I find they're always a pain to enable on projects because there are always so many pre-existing warnings, and you can never turn the warning you want into an error straight away because you have to fix all the pre-existing one first. So this kind of deployment avoids that issue. Okay, so that's more or less it. The current status is Infer runs on all diffs for Android and our iOS apps, as well as our C++ backend. And that represents tens of thousands of diffs every month. And there are thousands of issues fixed every month out of all the ones reported by Infer. And that's about a 70% fix rate. And the fix rate is what we measure as giving good signal to developers. It's the proportion of reports that were fixed by developers as they were reported by Infer. And that's the metric we take, and not some other metrics like false positives or things like this, because that's a metric we can actually measure. So that's why it's important to us. Okay, that's all I had to say. Thanks for listening. Any questions? Yes?
So back in the example with memory allocation, what if the allocation happens conditionally depending on one of the parameters of the function? Is the system smart enough to analyze the call side?
The question is, what if the allocation happens conditionally depending on the parameters passed to the function? I think for this checker is quite simple. I don't think it looks at this kind of thing. I think it would report anyway, but I'm not quite sure. But some other checkers we have, like the ones for memory safety, they try very hard to follow the values as well.
They do kind of subsolvers again that track which parameters will cause certain effects. And then
so one way to I don't know if this checker does this already, but the way we would do that would be to record two specifications for that function. One where some parameter, if x equals 0 as a precondition, then it doesn't allocate, and another of if it's not, then it allocates. And then at the call site, you can see in which branch you are. Yes, I believe you were.
So I have a good question of diff-based deployment. Help me understand if it's part of open source code base or is it something internal that you use?
The question is the diff-based deployment part of the open source code base or not? So at the moment, it mostly lives in our CI code and not in Infer. There's ongoing work about moving that logic inside Infer itself. So for now, there is part of it in Infer already, which is the part about comparing two reports and computing the lists of pre-existing and fixed and introduced buckets. Yes?
This is a follow-up. How is it linked, the two parts, the static analysis and the isolation of errors regarding the diff? How much are they linked in Infer, and how do you envision that it would be possible to reuse the diff analysis part for other static analysis tools?
So
in the CI context.
The question is how interwoven are the static analysis part and the diff analysis part. And at the moment, not at all. We just run Infer once, run Infer a second time, and then we do some logic just on the JSON report. So that's how it works. So it works the same way for all our analysis because it just works on the final report.
So it could be a separate project?
Yeah, it could be a separate project that works for other things as well. Yes?
So you said that when there is a warning, you don't warn if the warning is not in the diff itself. That sounds like a very bad idea, right? Because I have a library function and I break it, then the rest of the code is deployed, and the difference in the diff, so I will not.
Yeah, so the question is that we report only on the files touched in the diff, and isn't that a terrible idea, for instance, for libraries, because you're breaking all the clients and you don't know it? Yes, that's a good point.
So the question was, do you not process it in text, or sometimes you look at the whole?
So do we sometimes look at this? No, not at the moment. We don't quite know how we would surface these issues to developers or how it will run. So, yeah. So we're still figuring this out. We're trying to surface all the bugs to developers, for instance, all the pre-existing bugs in the code base. That's one way to do it, but that doesn't quite answer this question. Yes.
Last question.
Last question.
Which ones other source analysis, source code analysis tools do you use at Facebook?
Which other static analysis tools do we use at Facebook? I think we use a range of static analysis tools, but I'm not sure exactly which on what part of the project. We use Clang. Yeah, we use Clang Analyzer as well on some parts of the code. And yeah, we use a bunch of static analyzers. I'm not quite sure which, sorry. Okay, thanks everyone. I think that's